Hello guys, welcome back to my channel. Today I came up with a very important and an interesting video related to average velocity of an electron, which we generally call it as a drift velocity. How we can derive the expression for drift velocity, and what is the phenomenon that takes place inside a conductor when an electric field is applied. These two things we will observe in this video. So we know that when a conductor, if you take any conductor, I took a cylindrical conductor, and we will see the situation before applying some electric field. Okay. So what happens? The electron here is represented with a small dot. Let us take a copper wire. It contains roughly around 10 power 29 electrons per meter cube. This is a very huge number, and these electrons are actually moving in random directions and collides with the positive ions that are there inside the conductor. These electrons are moving with a velocity called thermal velocity. So this is a very high velocity, which is in the order of 10 power 6 meter per second. So with that very high thermal velocity, the electrons inside a copper wire or a conductor moves and collides with the neighboring positive ions, and during each and every collision with the positive ion, they will attain a new velocity freshly and again start to collide with neighboring positive ion. Like this, lot of collisions will take place inside this conductor, so that the electron will not be moved anywhere further. So the net movement of electron in this case, let me divide these two cases with the help of a line. So the net movement of electron is zero. Why? Because the electrons inside this copper wire are moving with very high velocities and collides with the positive ions which are there inside the conductor. And these electrons, because of these collisions, the net movement of electron is zero. Okay, if there is no net movement of electron, we can say that the current inside the conductor is zero. This is the situation when it is not connected to a battery, when the conductor is not connected to a battery, or when we don't apply any electric field. Now consider the second situation where we have applied some electric field. So here you can observe in the second diagram, the direction of electric field is towards the right, because the battery terminals are given in such a way that the electric field is towards right. Now we know that the electron movement is always against the electric field, so the electron try to move towards right. As the electric field is applied towards left, the electron try to move towards right. So what will happen now is, in addition to thermal velocity, it also have a drift. Now see, the electrons thermal velocities will not change and they will move in random directions, but what this electric field will do is, it will just create a small drift in the position of the electron against the electric field. So for example, let us say the electron here, it is here, it has to actually hit this positive ion. This is shown with a dotted line. Actually it has to hit the positive ion, but because of this electric field applied, because of that electric field is applied, the electron drift towards right a little bit and hit another positive ion. Okay, now After colliding with this positive ion, it actually has to hit this positive ion, but it will not hit this positive ion because of the electric field is applied during the time, means the time between any two successive collisions. So this one is first collision, and here you can observe the second collision. So between first collision and second collision there is a time gap, and we call this time gap as relaxation time. So during this relaxation time, the electron will be accelerated towards right, and we call this small shift in the position of the electron as drift. Okay, so instead of colliding this positive ion, it will collide this positive ion. Now, after colliding this positive ion, it will gain a new velocity, and actually it has to hit this positive ion. But because of applied electric field, it is hitting this positive ion. Okay, like that, what we can observe finally is, in addition to the thermal velocities of thermal velocity for each and every electron, there is one more force that is acting on it, and that force is force which is due to the electric field. And this electric field is making the electron to accelerate, because if you add all the thermal velocities, means if the electron is having only thermal velocity, then the average of all those velocities will be zero. But now we have both thermal velocities as well as a electron drift. That's why when you add these velocities, we'll not get a zero value, we'll get an average value, and we call this mean velocity of an electron or average velocity of an electron as drift velocity. Okay, so first we need to understand what happens in between the two collisions. In between any two successive collisions, the electron has to be relaxed, but during this relaxation time, the electric field comes into picture, and it will try to drag the electron towards right. So instead of hitting this positive ion, it is hitting this positive ion. Okay, now we need to, after having a knowledge on drift, what is meant by drift, now we need to derive the drift velocity expression for drift velocity. Okay, first I am applying some electric field, therefore on a single electron, we will see the situation with a single electron. The electric field applied will apply some force on an electron. That force is Fe, which is given by minus E times E, because we know that the relation between the force and the electric field intensity is F is equal to QE. Here the charge is an electron, that's why in place of Q I took minus E, which is the charge of electron. This is the applied force on the electron. Now this electron is accelerating in a particular time during the relaxation time. So I am just applying Newton's second law, and this electron has some mass. So according to Newton's second law, the same electric force is given by m times acceleration, where m is the mass of individual electron and a is the acceleration of this electron. And this acceleration takes place only during the relaxation time, means between any two successive collisions this acceleration is taking place. Now equating both the LHS terms will get RHS terms equal, therefore minus E times capital E is equal to m into A, and A is equal to minus E capital E by small m. Consider this equation as the first equation, which gives us the acceleration of electron under the influence of electric field. Now we need to find the average velocity of the electron. See what electron actually doing. See, the electron is coming like in this path. actually it has to come in this path, but instead of coming in this path, it is going to a different path, right? So let us assume that this is the first initial velocity. It has u1, okay, and this time is t1. From this point to this collision, the time is t1. After colliding with means before collision with the positive ion, it has a velocity, and we consider that as final velocity. Therefore the relationship of velocity of electron before the collision, means between any two collisions, if you consider the velocity before the collision as the final velocity, and the velocity after the previous collision, okay, see, before the second collision, if you consider that as a final velocity, and after first collision, you can consider it as initial velocity. Therefore you will have v1 is equal to u1 plus a into t1, okay. Similarly, for all the ions, means for example, if there are n number of collisions that took place, uh, for all the n number of collisions, you will have fresh velocity. Means after this collision, it will attain a velocity of u2, and before colliding this positive ion, it attains a velocity of v2. After colliding with this positive ion, it again gets a new velocity, and let us assume that new velocity as u3. Like that, we have initial velocities and final velocities after the collision. After the first collision, we can consider it as a initial velocity, and the velocity before the second collision is considered as final velocity. And again, after the second collision, we consider it as initial velocity in the second collision, initial velocity for the second collision. And before the third collision, we consider it as final velocity. Therefore v2 is given by u2 plus a times t2, and so on. And if you have n number of collisions, you will have vn is equal to un plus a t n, okay. Now, what is actually drift velocity? I have written the definition here. Average velocity of an electron when it is moving from one side to another side along with the thermal velocity is called as a drift velocity. Okay. Now, let me do the remaining thing in the next page. So, average velocity we want to find. Okay. So, let me find the average velocity. We take a separate color for this. So average velocity means the drift velocity, which is given by sum of all the velocities of the electron for n number of collisions by total number of collisions. In this way, you can find drift velocity. Now, in each and every value of v1, means in place of v1, what we can substitute? We can substitute u1 plus. If you observe the previous page, let me show you. So in place of v1, we can substitute v1, sorry, u1 plus at1. In place of v2, you have u2 plus at2. Here, if you observe, the acceleration is not changing. Why? Because we are applying a constant potential difference. Okay, as we are applying a constant potential difference, it will apply as a constant electric force. A constant electric force will make the electron to accelerate in a uniform way. That's why acceleration is constant here. So these are the values of v1, v2, and so on, vn. When you substitute those values in the equation for vd, in this equation, when you substitute those values, you will get u1 plus, let me write all the initial velocities first, u3 plus, and so on, plus un by n, and plus a times t1 plus t2 plus t3 plus, and so on, plus tn by n, okay. When you substitute those final velocities here, you will get this value. Now if you observe, what are these u1, u2, u3? All these are the velocities that the electron will attain after each and every collision. Means, see, after first, initially it has u1. After first collision it has u2 velocity. After second collision it has u3 velocity. So all these velocities are in random directions, so that when you add them, you will lead to a zero value, because all these are in random nature. Therefore when you add them, the summation will be a zero. That's why first term in the equation will become zero. So let me make this entire term to zero. Why? Because all these are the velocities attained by electron after colliding with the positive ion. Because these velocities are in random directions, the summation of all these velocities is zero. And let me go to the second term. Second term contains acceleration, and the term inside the bracket gives us the average of different times. What are those times? When you observe the figure, let me show the diagram once again. So in this figure, this is the time t1. So this is the time t1, and here you have time t2, here you have time t3. What are these times? These are the times taken by the electron to move from one collision to another collision. Means it is the time between any two successive collisions. Okay, it is the relaxation time, but actually relaxation time is the average of all these times, because we cannot say that t1 is equal to t2, t2 is equal to t3. Sometimes it will take 5 seconds, t1 may take 5 seconds, t2 may take 7 seconds, t3 may take 4 seconds. When you add all those times and take the average for that, you will get a time between any two successive collisions. We call this time as relaxation time. Okay, so the time spent by an electron between any two successive collisions is called as relaxation time, and that relaxation time is nothing but the average time, average of all the times taken for n number of collisions. So it, in this place, in the place of this entire term, we can substitute tau, because tau is nothing but the relaxation time here. So Vd is equal to A into tau. Now in place of A, what I can substitute? Let me go to the previous page. In place of A, from the equation 1, we can substitute minus E, capital E by M. Okay, minus E, capital E by M. So substituting that, Vd will gives us minus E, capital E by M into tau, where minus indicates just the charge of electron. As the electron has a negative charge, we kept a negative sign here. So the magnitude of drift velocity is given by E tau by M, where E is the charge of the electron, and capital E is the magnitude of electric field, means our intensity of electric field. Tau indicates the relaxation time, which is the average of all the times taken by the electron between successive collisions, and where m is the mass of the electron. Okay, so this is the expression for drift velocity. So in the next video, we will see the relation between drift velocity and current, as well as current density. I hope this video gave you a clear understanding of drift velocity, means the velocity of an electron between two ends of a conductor when an electric field is applied. This is the mean value of electron, or the average value, average velocity of an electron when it is traveling from one side to another side, having a lot of collisions. Okay, so if you really enjoy this video and really learn something, Please hit a like button and subscribe to our channel to support our efforts. Thank you very much.